welcome once again to what I believe is going to be one incredible 1 hour minus epsilon worth of a journey with, I guess, the perfect captain, pun intended, because of the backdrop, Professor Sylvester James Gates Jr., or Jim Gates, as he's referred to very fondly globally. So Jim is, of course, a theoretical physicist. He's currently the Brown Theoretical Physics Center Director, the Ford Foundation Professor of Physics, and affiliate mathematics professor, a faculty fellow, Watson Institute for International Studies and Public Affairs at Brown University. Earlier on, he was at the University of Maryland, College Park campus, and he was the University System Regents professor, as well as the John S. Toll Professor of Physics, and also the director of the String and Particle Theory Center, as well as the affiliate professor of mathematics. Professor Gates served on the US President's Council of Advisors on Science and Technology, contemporaneously on the Maryland State Board of Education from 2009 through 2016, and the National Commission on Forensic Science from 2013 through 16. Professor Gates is globally known for his work in SUSY, supersymmetry, that is, supergravity, SUGRA, and superstring theory. He received 2 BS degrees and a PhD from MIT, where his doctoral thesis was the institution's first on the topic of supersymmetry. And in 1984, he co-authored the book, which is, the book, has been the book for such a long time on superspace, supersymmetry, and it's in fact globally recognized as the first comprehensive book on supersymmetry. He is a past president of the National Society of Black Physicists and an NSBP fellow, as well as a fellow of the American Physical Society, the American Association for the Advancement of Science, and the Institute of Physics in the UK. In August 21, that is pretty recently, he was the recipient of the 2021 Andrew Gimant Award. He was elected as a fellow of the South African Institute of Physics, SAIP, beginning May 2021. And in March 2020, he was elected to the Mathematical Sciences Research Institute Board of Trustees. In 2019, he was elected to the presidential line of the APS, that's the American Physical Society, where he's currently serving as a president. He's also an elected member of the American Academy of Arts and Sciences and the American Philosophical Society. In 2013, he was elected to the National Academy of Sciences, becoming the first African-American theoretical physicist so recognized in its 150-year history. In fact, President Barack Obama awarded Jim Gates the National Medal of Science in 2013. From 91 through 93, Professor Gates was the chair of the Department of Physics and Astronomy at Howard University and served as the founding director of the Center for the Study of Terrestrial and Extraterrestrial Atmosphere, CSTA, SIST, I guess, funded by the National Aeronautics and Space Administration. His tenure also saw the inauguration of efforts leading to MHAT-CAT, which is the Michigan Howard AD&T Collaborative Access Team, to carry research at the synchrotron at the Advanced Photon Source in 1994, supported by the Department of Energy, DOE. During the academic years, including 2007 and 2013, he served as a Rydell Visiting Professor at the Gustavus Adolphus College. In 2015 through 16, he was in residence at Dartmouth College as a Roth Distinguished Scholar. I just want to squeeze in a personal note, which is that we were so fortunate, in fact, to have Professor Jim Gates over here visiting our campus way back in 2007. So the Department of Physics had organized a so-called IWT-HEP, International Workshop on Theoretical High Energy Physics. And we were again lucky to have Jim visit us in 2009 for a Tech Fest, Cognizance, or Cogni as we call it here locally. So I think with those words, I would very humbly request Professor Gates to please deliver his lecture. Professor Gates, please.
Thank you, Alok. Thank you very much, Professor Mishra. I wish you had not taken so long with the introduction because you've cut into my time for making my presentation. But that's a joke in case people are concerned. I'm always slightly embarrassed when people go through introductions. I've had a very interesting life in physics and out of physics. And I effectively have 4 simultaneous careers. So I've got and a family. My daughter is at Princeton now. She studies black holes, and her twin brother is still in graduate school. He looks like he's going to be a biophysicist. So we like physics in my family. So let's get started on my journey for today. So I'm going to share screen. And so the title, as you're probably aware, is People No One Can Imagine Anything Of, and following S. Ramanujan's example. Albert Einstein has once said that imagination is more important than knowledge, for knowledge is limited to all we know now and understand, while imagination embraces the entire world and all there will be to know and understand. Alan Turing, it is often referred to, said, sometimes it's the people no one can imagine anything of who do the things no one can imagine. And the source of this quote is a little bit in question, so that's why I have my notation there. So, Srinivasa Ramanujan, an amazing mathematician. So I wanted to focus my talk a little bit on asking the question, what is it that he was doing that those of us who are engaged in research that is enabled by mathematics might learn as a way to perhaps have just a fraction of the insight that he demonstrated during his life. Well, here's a familiar face, Albert Einstein. I tell people Albert Einstein is my hero maximus in physics. And one of the things about Albert Einstein, and here I have to thank my host, Professor Misra, because he asked me to give this talk, modeled on a talk I gave at the University of Southampton in England within the last year. And they asked me specifically to pay attention to Albert Einstein's concerns about diversity and outreach that he personally made to the African American community. So you can see here a picture of Albert Einstein giving a lecture. But as you can also see in this picture, all of the students are African Americans. This was in 1946, where he received an honorary degree. And he gave a very famous speech in which he said that racism is a disease of white people, and he was not going to ignore it. I mean, a very provocative statement, but he made it. It's little known, but if you want to learn more about Albert Einstein, you can look at some of the other people that he had contact with. This is a picture of Albert Einstein and Mary Anderson. She's a great contralto opera singer. And when she first was invited to Princeton to give a concert, the hotel in Princeton would not give her accommodations owing to the fact that she was Black. Albert Einstein had met her earlier and had just been amazed by her talent. And he heard about this. And so he invited her to come and stay at his home with his wife and housekeeper. And on a subsequent visit, she also stayed there. So it's clear that Albert Einstein was not someone who had bias against people of other races. Although he's not perfect, there are no perfect human beings, but a lot better than you might imagine. If you, this is the story about Albert Einstein, so I've recited that. But if you want to learn more about Einstein and his views on race, there's a book that you can get. The cover is on the screen now, On Race and Racism, authored by Fred Jerome and Roger Taylor. Back to Ramanujan. As most people know, and certainly in science, Albert Einstein spent some time as a clerk. Well, although not quite as famous as Albert Einstein, perhaps though subconsciously he is, Ramanujan also spent time as a clerk. And so I like to call this part of my talk another clerk no one could imagine anything of, who did things no one could imagine. If you, as I said, I suspect this audience probably knows more about him than I do, but I want to just go through some things. So in January, G.H. Hardy, English mathematician, received a package of letters, And in them was a letter that began, "Dear Sir, I beg to introduce myself to you as a clerk in the accounts department at the Port Trust office in Lagos on the salary of only £20 per year. I am now about 22 years of age." And they went on to say that he had made startling progress in the theory of divergent series in mathematics and had all but solved the long-standing problem of the distribution triangle. The cover letters ended being poor. If you are convinced, and he went on to state that that he would like to have the opportunity. And he also included 11 pages of technical results that range over mathematics. And I like the page I'm showing you. Oops, I'm sorry.
Jim, sorry, I apologize for interrupting you. There seems to be some sort of a audio clarity issue at your end. I mean, there is the audio is not too great for some reason.
Okay, give me a moment. Let me see if I can. Give me a moment. I'll try to.
Yep.
Is it any better now?
Is it better now? It is better. It is better.
Okay, I turned my volume up. Okay, so today, so as I was saying, so one of the results that Ramanujan forwarded to Hardy is at the bottom of this page. And this result turns out to be incredibly important for modern day physics. It's that the sum of the positive numbers is equal to minus 112. But if you multiply 12 by 2, you get 24. If you add 2 to 24, you get 26. In fact, this formula is the reason that it is said that the bosonic string exists consistently in 26 dimensions. So Ramanujan's results have a direct relevance to physics now discussed these days and likely into the next century. He also, today, you can actually use Mathematica or Wolfram Alpha to check these results, at least numerically. And so it's amazing to ask, how in the world was this work from India? Because when Hardy contacted him, remember at the time of the British Empire, no one in Britain expected this sort of brilliant mathematician to emerge. The Royal Society has a display that I would commend to your attention. You can see the URL at the bottom, and it goes through some of Hardy's interactions with Ramanujan. And it's a very nice display, and I recommend it highly. These are some of Ramanujan's original writings that we're seeing. And he made a series of quotes that I found very interesting. Let me go to the last two on this page. While asleep, I had an unusual experience. There was a red screen formed as it were, and I was observing it. Suddenly, a hand began to write, and I became all attention. That hand wrote a number of results in elliptical intervals that stuck to my mind. As soon as I awoke, I committed them to writing. Then finally, the most famous quote that I'm aware of. Sir, an equation has no meaning for me unless it expresses a thought of God. Now, it's been said that he was practicing something that you might call it an experimental approach to mathematics. I would actually add another word. I would call it an experiential approach to mathematics. And again, for people who wish to explore these topics further, I have some links here. So that's my background on Ramanujan. And we're going to come back and find out why that's relevant to this talk. So Albert Einstein is the person that told us that space and time are not separate, but that they can be mixed. And the equations that you see in front of you are basically Lorentz transformations, written in terms of hyperbolic trig functions, because that's the natural way to write Lorentz transformations. I give a lot of talks to people who are not as technically trained as this audience, so I like to rely on visuals. So what do those equations that we just saw mean? Well, it means that space and time is flexible. Now, if you look at this video, you'll notice that there's only one thing that's constant in this field. That's the slope of the yellow lines. You can think of those slopes as the speed of light. And so those transformations that we were seeing correspond to the deformations of the blue space-time manifold, but you'll notice the only constant thing is the speed of light. He did a second great thing in 1915. What we just reviewed was 1905. But in 1915, he came up with the theory of general relativity. And we know how this started because he was still, although special relativity began in 1905, in 1907, he was still a clerk. And so he tells the story that one day he was working, he looked out the window, he saw someone working on the roof in the barn, and he realized that if one of them fell, he would not feel his weight. And Einstein called that the happiest thought of his life. Why? Because that thought impelled him to construct the theory of general relativity, which I've written as a shorthand for you on my screen. So what do Einstein's field equations tell us? Well, they tell us that basically space and time not only can flex, but that they also can create waves. And dimples. So in this cartoon, we see the dimple representing the gravitational force from the sun, which keeps the Earth in orbit. And around the Earth, we see the dimple in space-time that keeps the moon in orbit about it. And that's the graphical representations of Einstein's great equations. Why is Einstein so famous? Well, a few years ago, about 2 years ago, I and a colleague named Kathy Pelletier wrote a book about how Einstein was brought to the attention of the world, not just to scientists. The book is called Proving Einstein Right. And what it does is trace the history for a decade of people watching eclipses. What you see before you are the paths of the eclipses that occurred between 1900 and 1920. And each one of these could have revealed that general relativity is an accurate description of nature, but it was the 1918 expeditions that led by Sir Arthur Eddington that actually did that. Our book is actually not about the science, it's about the people who did the science. So if you want to know what real people do in their lives to do great science, I commend this book highly to your attention. The net upshot of Einstein's equations is we believe we have a scientific basis for explaining the entire universe in which we live. That's an amazing accomplishment. His equations actually predict that the universe could have started in one of 5 different ways, not a single one. What I'm showing at the top is the so-called cosmological zero solution. And in that case, the universe could have come into existence, but depending on whether there's more energy in the gravitational field or the matter fields, you might have had a universe that expanded forever, which you see on that. But you might, if the majority of the energy was in the gravitational field, the universe would have actually stopped expanding and recontracted. So that's one of the solutions. We also have the so-called cosmological solutions, which you can see. And in fact, for a long time, for most of the life of Einstein's theory of relativity, we thought we lived in the land of zero sector of his equations, but now we live in the land of equal less than zero. In almost every classroom around the world, there's a science class. You can look on the wall and see a symbol, and it is the Mendeleev table of elements. It doesn't look like this. However, this is what Mendeleev's original table of elements looked like. And you can see there are holes in this schema, and he used those holes to predict the existence of new elements which had not been seen before he organized this table. So it turns out that these kinds of artistic symbolic representation are extraordinarily important because they can tell you things. And here's our modern table of elements, all the holes that have been filled up. It has been greatly augmented by discoveries. But remember, Mendeleev actually did this because he figured out how to organize elements. These days, we have something called the standard model. And this chart that I'm showing you here is not so as common in high school classrooms as the chart of the Mendeleev element, but it could be because it tells us what the elements themselves are made of. We have on the left side of this, the electron, its neutrino, the muon, its neutrino, the tau particle, its neutrino. It's about leptons. But then we have quarks, up, down, charge, strange, top, and bottom quarks, which are the constituents of protons and neutrons. Then we have the force carriers, the photons, the electromagnetic force, the W plus and W minus and Z0 for the weak nuclear force, and 8 force carriers for the chromodynamic force. And so this could go to the classroom and say, behind the table of elements, there's this other table. However, in 2012, a new element was added, a new component was added to this table. Namely, we discovered the Higgs boson, which had been anticipated for over a decade by the mathematics that describes elementary particle motions. Oftentimes, if you go online and look for particles of standard model, you see an image that looks like this. And if you look at this, it's actually pretty symmetrical. These particles have different spins, so let's spend some time looking at that issue. The Higgs boson I talked about. Its importance was most, its discovery was most important because these yellow and blue balls that you see at the bottom, for the little white ball, that stands for the photon. The big blue ball over here stands for the W, plus and minus, and the yellow stands for the Z. You see, before 2012, we didn't have a consistent mathematical way of describing how the bosons here and here get their mass. There was a theory that was started in the 60s. Sir Peter Higgs was one of the authors, but it turns out there were about 12 different people that actually made contributions to what we now call the Higgs boson theory. And the net result is we now know how to have massive Z's, massive W's. I think I misspoke before, the W's are here. And it's all because the Higgs boson can be thought about as rolling down the energy surface to a minimum. Well, the Higgs boson is a spin zero particle. That means if you describe its motion, the differential equations involved look all remarkably like the equations that you would describe for disturbances on a slinky. So I have a picture here of a slinky to bring this to our mind. There are also other particles in our table. I'm sorry, could someone mute? Could someone mute? Thank you. There are other particles in our table elements, and they also have spin, in particular electron spin. And so they behave as if they're little balls, but that you shouldn't actually think of this, although this is an analogy, and it captures the mathematics. You shouldn't think of this as that electrons spin in the sense that we can see, because they don't. The mathematics is rather different. And in fact, part of that difference is illustrated by this chart, because you can imagine at the center of these spheres, there are electrons that are moving upward, and you can ask, what axes are they spinning along? And let's assume we have an ensemble of such electrons. Well, particles in that ensemble moving vertically could have their spin vector any place along the direction of that latitude that you see that the blue arrow is pointing to in the left-hand picture. Or they can have their spin vector pointed anywhere along the latitude that you see in the right-hand picture. But they cannot have this axial spin in any other direction. This is part of the mystery of quantum. The photon has spin. So this is something that classically we call polarization, but it's really an intrinsic spin property, much like the property of the electron, except that the rate is twice as large as that of the electron. When you study the mathematics of spin, you begin to realize, and this was done in the 1930s by Fritz and Pauli, that particles can actually spin at far more diverse ways than people normally think about. So this is an illustration not of a spin 1/2 particle, but a spin 3/2 particle, again, moving vertically as you look at these pictures. The particle, you should think of it as being defined at the center of these spheres, and its spin vectors can only point along the latitudes that are indicated in this diagram. What about the graviton? Well, it also has a spin. Again, this can be seen classically by studying the analog of polarization that we study for electromagnetism. Gravitons can possess polarization. So here, in this cartoon, again, something I found at YouTube, which is quite useful. I want you to imagine being in a circular tunnel and looking down the tunnel. That's the circle that you see here. When a gravity wave comes from the back to the front of the tunnel, it causes deformations of the walls. And you can see those deformations here. Now, of course, in reality, you can't see these deformations because the actual motion It's on the order of 1/1000th the size of the nucleus of an helium atom. But this gives you a general sense of how you might go about thinking about detecting a graviton wave. Now, this is linearly polarized gravitational waves, but you can also have holistic positive circular polarization. As you can see, our tunnel undergoes a much more ballet-like set of motions than in the first case. And if you can have positive helicity, you should expect negative helicity. Now, we have detected waves of gravity at the LIGO facilities in the US and Virgo in France, which is a French-Italian collaboration. And these instruments have allowed us to see waves of gravity for the first time in history. However, these instruments have not measured the spin of the graviton, the thing responsible for those ballet-like motions that I showed you. That's going to be the next scientific challenge in gravitational wave physics. Now, it's very important to verify that the graviton performs those motions as it moves that I showed you, because those motions are predicted by Einstein's field equations. So it's another challenge. Did Einstein get it right or get it wrong? And in physics, the way we satisfy ourselves for answers is we do experiments and perform observations. Science is really about what humans can observe and measure. So remember the table of standard particle model I showed you? It looks nice and symmetrical, but it doesn't look symmetrical if you start asking questions about the spin. That nice symmetrical image I showed you earlier actually breaks up like this. Down here we have the quarks and the leptons. Those are the things that matter is made of: atoms, molecules, chemical elements, and us. On the other hand, in this quadrant, we have the force carriers: 8 gluons, the photon, the Z particle, the W plus and minus intermediate vector photons. This one carries a strong nuclear force, electromagnetic force, these two the weak force, and the Higgs boson, which is also a carrier of the weak nuclear force. Now, when you look at this table, my claim is that most people would say this is not very balanced. And what we mean by balance is a lack of symmetry. And so, how can we make it more balanced? Well, remember the Higgs particle was only discovered in 2012. Let's imagine that we go forward in time, say 100, 200 years. Might more such particles be discovered? Well, so the answer is probably yes. And it might be the case that 200 or so, maybe 300 years, you might have this set of particles. You'll notice this is beautifully balanced left and right. This is a picture of what the standard model looks like if you include the principle of supersymmetry. And Alok was kind enough to mention that I wrote MIT's first thesis on this topic in 1977, and a comprehensive book in 1984 along with Mark Vissler, Martin Rochek, and Warren Siegel. So maybe at some distant point in the future, we'll see that the standard model gets much expanded, just like Mendeleev's initial table was expanded. We also have in our world classical, not just classical physics of Newton, but quantum physics. And so I've used this illustration to show you that Newton says, if you tell me the velocity and the direction of an object and tell me no forces are acting on it, it moves along a straight classical path. If you do quantum mechanics and you give the same information, there are actually an infinite number of paths that the particle can move along. I've shown you one in this diagram. They're jagged, they're piecewise, continuous. It's amazing what quantum mechanics allows. And it only says that you can take probabilities of these different paths. So the classical path, well, like I said, that's Newton's second law. Everything's you put it in there. And you can apply that to things like electromagnetism, and in fact, Coulomb did. And Coulomb's law is a statement that we, in modern language, can think of as the following story. There are two electrons at the bottom of this image. One of them moves along and it emits a photon, which carries the message to the second electron that the first electron is close by, and that the two need to move apart. So here's the force carrier, and here's the matter particles. So this is like what classical physics tells us. Now remember the quantum path that I told you about? Well, it tells us a lot more complicated and interesting stories. So in fact, our two electrons might do the following. The first electron moves along and emits a photon, which travels to a point in space-time where my cursor is pointing toward. And at that point, the photon disintegrates into a positron and an electron. In other words, a particle-antiparticle pair. Particles and antiparticles have opposite charges, so they would be attracted back to each other. And at the second point where my cursor is pointing, the particle-antiparticle pair has now recombined to a second photon, and it's this second photon that carries the message you ought to be. Now, this kind of picture is actually a Feynman diagram. If you take relativistic quantum field theory, you'll learn how to calculate the integral expressions and the force laws that are associated with this picture. But not only this picture, there are an infinite number of such pictures. And those are what we could refer to as the quantum corrections to the classical physics. If you replace the electron by a muon, and then instead of forcing the electron-positron pairs to move around the loop, you get this diagram. And this diagram is actually related, we think, to some very interesting physics that is occurring right now. The muon, which is in the family with the electron, which is basically an electron but 200 times its mass, and has a magnetic moment. The classical value of that magnetic moment is the number 2. All of these small digits that you see following this are coming from Feynman diagrams. And in fact, hundreds of Feynman diagrams contribute to the current measurement. The ones I'm showing you are about a decade old, so these aren't that current. And in April of last year, it was noted that the magnetic moment of the muon looks like it needs contribution from those loops that I showed you, but the particles in those loops are not standard model particles. Now, this is astounding because maybe some of you know that starting in 2008, a device in Geneva called the Large Hadron Collider started looking for particles. Many people expected super partners, that balanced picture I showed you. They thought the first one of those particles might be discovered. I thought that was unlikely. And I said so in an article in Physics Today entitled "Is String Theory Phenomenologically Prior?" So this excites me. In fact, in that article in 2006, I said you should be looking to precision experiments, not the kind of what's called direct reduction that the vast majority of our community committed to in building the LHC and then searching for superparticles. Well, we talk about quantum, but quantum must also affect the realm of gravity. So on the right-hand side of this image, I have Einstein's general relativity. On the left-hand side of the image, I have Einstein and quantum. You might wonder what Einstein is doing on the left-hand side because it's famous that he never made his peace with quantum theory. Well, you see, in 1905, Einstein wrote a paper on so-called photoelectric effect. And that paper was one of the first papers that impelled quantum theory into existence. So even though he didn't ever make his peace with it, he had made a contributions to it coming into existence. So the standard model, those collection of particles I showed you, is mathematically what's called a fiber bundle. And you can see sort of a cartoon of a fiber bundle here. At the bottom, this sheet that we see, you can think about that as being where space-time occurs. According to space-time, label where you are on the sheet. The force carriers are related to saying that there are these tiny thread-like objects that are related to our manifold. And there are 3 classes of them. There's the electromagnetic set of threads. There are the SU3 set of threads, and there are the SU2 cross U1 set of threads. And so it looks like this is the structure that well, we know that mathematically the standard model comes from the structure. Now, in the 90s, 80s, 90s, and early 2000s, enormous amount of energy was spent looking at string theory. And most people think of string theory as a higher dimensional theory, but I happen to know that you can have 4-dimensional strings. As long as 3 other physicists, such as Dieter Roost in Germany and Henry Tai at Cornell, we all showed that the string theory of mathematics actually admits only 4-dimensional theories. These are almost never studied, but they do exist. And what that means is that string theory can be made to be consistent with the mathematics of the standard model at fiber bundle. It has three different sectors. The top sector is where energy, momentum, angular momentum are described in terms of string theory. These string variables here are not 10-dimensional string variables. They are 4-dimensional string variables. These are variables describe the different gauge groups, those fibers that I showed you. And then the mathematics of this final group. Remember we saw copies, that the electron had a copy called a muon. It has another copy called a tau particle. Well, in string theory, you can actually see the origin of those copies by this sector of the string. In 1995, Ed Witten, who I was informed spoke to this meeting recently, yesterday, made a stunning suggestion. He said that if you want a quantum theory of gravity, one place you might want to look is unifying all strings into what he called M theory, or what has been come to be called M theory, and study the mathematics of that. Well, it turns out it's much simpler than the mathematics of the standard model. You can see there are only 3 functions that we have to worry about. But these 3 functions actually have some interesting properties. If you study them on the classical path, it turns out that the number of degrees of freedom of this, which is a fermion, and you compare against the number of degrees of freedom here, these are bosons, those numbers of degrees of freedom actually balance. And that's what supersymmetry likes, is balance. Remember our balance picture? But if you don't follow the classical equation motion, you don't get balance. And so one of the problems that's left over from Ed's suggestion is how do you restore that balance in a way that's consistent with quantum theory? I'm going to speed up a little bit here. And so this question has been around since Ed Witten's 1995 suggestion, but it could have actually been asked right after a theory called 11-dimensional supergravity was constructed. So what's the puzzle? Well, in science, particularly if you've learned calculus, you learn about these things called Taylor series. So when Ed and the people who constructed 11-dimensional supergravity started, at the basis of their work are these Taylor series expansions. But these expansions go to really high order. In fact, you can work this out, well, you can work generally with the form out, but what you can't work out from the original mathematics is what are the spins of these higher order terms? Remember those different wiggly shapes that we saw? Well, they would have to occur here, but for over about 40 years, no one knew how to describe those, what I like to call wigglers. And so in 2004, I started thinking about just solving these equations in a very different way. Namely, instead of thinking about equations, let us turn our attention to graphical images. So along with Michael Fox, I created a new piece of mathematics that we gave the name to Adinkras. We found this piece of mathematics by applying Einstein's idea about the structure of space-time, where there's a future light cone, a past light cone, and observers are only at a single point. And in 2010, our work was actually highlighted in the British Journal Physics World. And so what our approach does is take equations, which you can see on this slide, these are differential equations, and it turns them into graphs. We are capturing elements of equations in these graphs, and it turns out that the graphs are so faithful that we can actually solve problems with them. I'll come to that shortly. These graphs themselves lead, if you're sort of artistically minded, lead to other more complicated graphs, but there are rules for creating these things that you can put on into a computer. And a colleague of mine named Greg Landweber did so, and you're looking at some of the pictures that come out of this mathematics. And so instead of thinking about Taylor series expansions, I started thinking about pictures. Now, these pictures capture the properties of the calculus that I showed you. So for example, those of you who take group theory know that there are these things called Youngkin rows. There are actually rules for how you take pictures like you see here on the left-hand side and get answers of different pictures on the right-hand side. And so these wigglers can be represented by these boxes. More multiplication rules, just giving some examples. And so given that this pictorial basis existed, I started thinking along with my students of how these pictures could lead to results that you could not derive using the Taylor series. So we use graph theory and network structures. We use a piece of mathematics called interlabels, Pythism, and we use a lot of computer power. Why do we need so much computer power? Well, that Taylor series that Ed Witten's suggestion suggests indicates is important leads to 2,147,483,648 bosonic degrees of freedom and an equal number of degrees of freedom for fermions. And remember, supersymmetry likes to have balance, so that's why these two numbers have to be the same. But as I said, we know the numbers of degrees of freedom, but how do they wiggle? That's the question that no one could answer. Well, in 2020, working with two of my graduate students, Hazel Mock and Yandre Hu, we figured this out. But we figured it out not from the calculus-based Taylor series, but by studying properties of these objects, which are they're polytopes, but they're kind of the mathematical version of crystals. Once you understand the rules for constructing these crystals, then answering the Taylor series problem turns out to be nothing but turn the crank with a computer. And so we were able to analyze all of the wigglers, and we can tell you at each level in the Taylor series expansion how many wigglers occur and how they wiggle. In other words, their spin. The data comes out in the form of information like this from the computer. These are so-called Dinkin weights, and Dinkin weights are a map from strings of ones and zeros to the kind of spin that you see. So it's very beautifully adapted for use on computers, although Dinkin weights are, in fact, an independent subject that mathematicians discovered having nothing to do with computer science. So on the formal side, I think the tools for projects for the future will include algebraic geometry and topology, graph theory, information theory. And let me talk about information theory because in some of my research, we were able to show that error correcting codes, classical error correcting codes, show up in the representation theory of supersymmetry. And then finally, computer-aided conceptualization. Remember, I told you need to use computers when you start getting numbers in the billions and trillions, but it's possible to master such systems. And then finally, evolutionism may play. So there's a race on to build quantum computers. And so I like to tell physicists, even theoretical physicists, that we all need to learn how to use this technology because it's amazing. I and my students could have never solved this problem that was posed by Ed Witten and the creators of love-dimensional supergravity unless we had access to computers. And by the way, it didn't take supercomputers to analyze these systems of billions of nodes. In fact, the algorithms we wrote ran on laptops. But the point is, in order to formulate those algorithms, you actually have to have an efficient way to picture a problem, and that's what those graphs do. I'm currently studying something called the hexapentaed, rumcicated, truncated seventh simplex. It's a relatively simple thing compared to summer problems. It only has 40,000 nodes and only 141,000 or so edges. And we're studying this because we're trying to look at supersymmetry, not in 11 dimensions, where Ed created M theory, but we want to know about how this relates to four-dimensional physics. So I and a group of my students continue to study these things. Here's a picture of the hexapentaed, rumcicated, truncated seventh simplex. And you can find this, for example, at the Wikipedia. It's an extension of this object. These things are called permutahedra. Again, these are topics in pure mathematics. And in fact, I have to tell you that I was watching a lecture from, I think it was the Tata Institute, if I remember correctly, about 2 years ago. And a French mathematician was talking about the permutahedra. And one of my graduate students told me, you need to look at this lecture. And essentially from that lecture, he was able to draw this picture. I looked at this picture and I went home. And that night, I had a dream. In the morning, I went back and told my student, if you calculate, there's a certain calculation that if you do it in this picture, it will lead to the same result no matter how you make the calculation. In physics and math, we call that an invariant. And so what was the calculation I was telling him? Well, we noticed that there are 4 light blue listings here. There are 4 dark brown listings. There are 4 purple. There are 4 dark blue and 4 green. So the calculation that I told him about was take any one of the green nodes and count the number of links to the other 3 green nodes in the picture. I'm not asking you to do it, but you know, if you could do it. Now take pick any light blue node and count the number of links from that node to any other light blue nodes in the picture. And do this for all the different colors. Now you might not be surprised that those all lead to the same number. I'll let you do the calculation sometime to figure out what that number is. But the big surprise was that now pick, say, the light blue node at the bottom and count the number of links to any of the orange-brown nodes. It turns out that those also yield that same number as the previous calculations. And this is true for any pick one and then go to the same color form. Now, the thing that's odd is that, as I said, I had a dream over the evening. So the next morning I went back and I told my graduate student, if you do the calculations over all of these, you're going to find the same number. And I didn't do the calculations. I just knew this was the answer. And after a couple of weeks and writing a computer program, my student came back and said, you're right. And we're going to come back and talk about that in a moment. These Bermuda are very interesting objects. And we're the only group in the world that has recognized this relationship between this mathematics and supersymmetry. So we're using this to explore further properties, like we were able to derive the answer to that question about the Taylor series using non-calculus-based mathematics, discrete mathematics. So these are collections of what we call super multiples. And it turns out that once you figure out the mathematical rules for these things, you can begin to derive things about that object that I told you, the omni-truncated 7 simplex. And some of my undergraduates are doing that. And so, why did I talk about this last part? And what in the world does that have to do with Ramanujan? Well, Ramanujan is famous for talking about how mathematics came to him in dreams. And it's not that I'm claiming I am Ramanujan, far from it. But my experience with that example is not the only time in my life when interesting things have been in my mind after a good night's sleep. And in fact, I often like to reflect that many people know that if you have a problem and you go to sleep, often in the morning, a solution is in your mind. And so what does that tell us about the human mind? Well, my suspicions are that our subconscious is actually completely capable of doing mathematics. This is a very strange thing to conclude. But I've experienced, as I said, things like this, not as much as on the scale of Ramanujan, but it has been a recurrent theme in my life that I've awakened in the morning and known things mathematically, not just arbitrary things. In the case of that I just showed you, the calculating that number, I knew that answer, and 300 calculations later using a computer, my student had verified the answer. Now, if you read about Ramanujan, you'll see that people say that he often had results that he made the claim came to him in dreams. And then what he did is actually check them. Well, maybe he's the first example, first and most extreme example of the way the human mind, even at the level of subconscious, is capable of doing mathematics. Now, I have often wondered about this in reading about him and then experiencing how I solve problems. As I said, I don't get it twisted. I am not comparing myself to him. He was an extraordinary individual. But the process that he described, I suspect many, many of us at much smaller scales also experience that process. And if that's the case, then it tells us something very interesting about solving mathematical problems. Namely, that we have a mode for solving these problems, which looks very similar to dreams or meditations. It's when a problem becomes so deeply embedded in our emotion, a different part of the brain kicks in and provides answers to relieve the emotional pain. That's what I think is going on. It's an amazing thing And I hope many of you get to experience this. So here I have my acknowledgments for the talk. Some of the graphics I use are coming from a product I produced for the great courses called Super String Theory, the DNA of Reality. And the creator of those CGI units was Mr. Ken Griggs. Also, some of the movies I showed you were created actually by my son, Sylvester III, who looks like he's going to be a biophysicist who will join his daughter who studies black holes. And that's all the kids in my family, folks. And that's all I have to say for you.
Thanks. Thank you so much. Thank you so much, Professor Gates. Maybe we could have a round of applause for that incredible lecture. Thank you. So I know you're running late for your APS meeting, but with your permission, maybe we could squeeze in a couple of queries. Will that be?
Yes, okay? Yes. I actually warned them I might be a little bit late. So have at it.
Okay. So all right. So there is a query by Kumar Ashutosh, and it says, "What if the disbalance, okay, the appearing in the Sugra is inherent to the physical world itself, and we are just trying to balance it out of habit?"
Well, that's something to recognize as a possibility. But if you look at the history of symmetries, we've never actually found a deep symmetry that nature herself didn't make use of. That suggests that having discovered supersymmetry as a remember, although I talk about this as balance, that's not how it was discovered. It was discovered using differential equations and Lagrangians and quantum field theory. That's how supersymmetry was discovered. So this balance aspect is simply a metaphor that allows me to easily explain what are the essential questions that are being answered. So it's not that, oh, we're just trying to balance a picture. That's not what happened. So yeah, it could be possible, but I suspect that won't work out.
Okay. I could ask a small query of my own. So I mean, this amazing work that you have started, especially the Adinkras program, the Prometeo-Hedron program, and so I mean, it's a beautiful pictorial way of understanding representation theory and supersymmetry. So I was wondering, I mean, you already talked about the fact that there could be possible connections with the algebraic geometry and the likes. So I was just wondering if this entire program could be encoded / decoded / reworded / reoriented, etc. in terms of I don't know, something in geometry.
Let me suggest something modular. Are somehow modular forms behind all of this? That's the way I would put the question. And I suspect the answer is yes. If you look at a lot of the work that is going on in theoretical physics right now, for example, the amplitude hedron that Nima Kanehama talks about, or cluster algebras, or the celestial approach to scattering amplitudes, all of them have a common theme of graphical, that they can be represented in graphs, and then basically these are objects that are algebraic topological. And so what the work that, like I said, we didn't do this work actually we did this work before people started talking about the Prometeo-Hedron, the amplitude hedron. So we didn't do this to try to glom onto a theme that we saw. We were simply trying to answer the question, if you look at SU3 theory, we know that polytopes are there. There are these diagrams where you see triangles and octets and all those pictures. Those you can think of those as mathematical crystals. And so the question that puzzled me for decades is, why haven't we seen the crystals that underlie supersymmetry? And that has driven me to this point where we discover these really weird and bizarre connections to mathematics.
Very good, very good. Okay, so I think we should not keep Jim.
No, as I said, I'm willing to take a few more questions because I did send an email message just before we began that I'd probably be late to my next appointment. So I can take a few more questions.
Okay, so it seems I'm not seeing although it was conveyed that we can have questions put on the chat session, but apparently people have been a little miserly in using that option. I don't see.
Okay.
So maybe I could be ask you one more question because
Sure. I have 2 minutes. Go.
great. Okay. So the pictures that you draw, and especially the language that you use, almost cry out to me that, hey, why don't you try out toric geometry and map the problems? You already, in some sense, addressed this in the previous query of mine, but maybe, mapping representation theory to singularities in toric vibrations, for example, in internal geometries relevant to string and M-theory compactifications. Do you think that could possibly have?
It could, because I have to tell you, maybe 10 years ago, working with my collaborators, and by the way, I need to acknowledge all my collaborators. I have a galaxy, and anyone who actually goes to the archive to look at papers that have my name, this is my collaborators. And one of my set of collaborators is a set of mathematicians. And one of them is actually an expert on toric varieties. So yeah, there is a real possibility that somehow such a mapping could be done. I haven't explored it because it's not on the main line of the question that I've set out to answer, which is I want a complete polytopic theory of representations of supersymmetry. As I said, I've essentially been pursuing that for decades.
Okay, so I think let us thank Jim once again for that amazing journey. Remember, I had told you that that's what lies ahead, and I think it was truly a beautiful combination of philosophy, physics, mathematics, sheer visual imagery. I mean, it was amazing. So thank you so much, Professor Gates. It was such an honor and pleasure for you to kindly agree to give a talk here as part of our Institute Research Day, celebrating the birthday of Albert Einstein, and of course, Pi Day. Thank you. Thank you so much. Thank you.
Thank you. Thank you for the invitation. Let's thank Ramanujan also, because he sits behind all of this.
Absolutely. Thank you. Thank you. So we